Welcome to Trapezoids and Kites, a geometry video lesson by Mr. Pi, the math guy. Hey, that's me. Obviously, we're going to be talking about the properties of trapezoids and kites today. Let's get right into it. Here we're discussing the basics of a trapezoid. We're asked to name the base angles of a trapezoid. Here in the black, I've written base angles are on the same base. The bases of this trapezoid are base AB and base DC. Therefore, the base angles are angle A and angle B, then angle C and angle D. The sides that are considered the bases are the parallel sides. The non-parallel sides are the legs. So that's how we can identify base angles of a trapezoid. Here we have a property of a special trapezoid, an isosceles trapezoid, in the form of a theorem. The theorem reads as this: the base angles of an isosceles trapezoid are congruent. So the angles that share a base in an isosceles trapezoid are congruent. So that gives us a relationship for writing equations when we have to solve problems finding the angles of isosceles trapezoids. We know that since the base angles, in this case angle X and angle Y, are congruent, they would be equal to one another. And the same relationship happens with angle W and angle Z because they're base angles. Over here in the orange, and that's what I got written here in the purple, since the bases of the trapezoids are parallel, the two angles that share a leg are supplementary, and that's what I got over here. This is the angles that share a leg. These are the angles that share a leg, and they are supplementary because they're same side interior angles. When you have two parallel lines crossed by a transversal, the same side interior angles are supplementary. And these are really two big relationships with angles in the world of geometry. Either they're congruent or they're equal, or their measures add up to 180. They're supplementary. So angles that share a leg and isosceles trapezoid are going to be, or in any trapezoid for that matter, are going to be supplementary. We're going to see how to use this theorem and property to solve problems involving trapezoids. Example 1. Quadrilateral XYZW is an isosceles trapezoid, and the measure of angle X is 156 degrees. So I'm going to stick that in here right now. And if you ever run across a problem where you do not have a diagram, making a simple diagram is going to make life so much easier. We need to find the measure of angle Y, the measure of angle Z, and the measure of angle W. Why having a diagram is going to make it easier? You're going to be able to visualize the relationships here. What I mean by relationships is this: to find the measure of angle Y is really simple if we use the property we just learned about. The base angles of an isosceles trapezoid are congruent. So the measure of angle Y is equal to 156 degrees because the base angles of an isosceles trapezoid are congruent. Now we can either find the measure of angle W or the measure of angle Z next. Well, really, what we're going to do finds the measure of both of them because they're congruent. So we could say that the measure of angle W is equal to the measure of angle Z because the base angles of an isosceles trapezoid are congruent. And that's going to be equal to 180 minus 156. Now the reason it's 180 minus 156, the angles that share a base are supplementary because they're same side interior angles. So 180 minus 156, that gives 24. So the measure of angle W and the measure of angle Z is 24 degrees. And here would be some work to justify that. Example 2. Half a spider's web is shown below, formed by layers of congruent isosceles trapezoids. Find the measures of the angles in trapezoid ABCD. Now, it is an isosceles trapezoid, so what we're going to be able to determine is that angle A is congruent to angle B because they're by definition base angles, and angle C is going to be congruent to angle D because they are also base angles. This problem starts down here along that line. That's a straight angle, so it has 180 degrees in it. Because it has 180 degrees in it, we're going to be able to calculate the measure of any one of these angles in here, because since these are layers of congruent isosceles trapezoids, this becomes a layer of congruent isosceles triangles. So we're going to know that the measures of each of these angles are equal because they are congruent. So since there's 6 triangles in here, we take 180 degrees, we divide it by 6, and that gives us 30 degrees. So we know this angle in here is 30 degrees. Over here I'm going to show my work or my justification. Let me write that a little bit better. That didn't turn out so well, that 30 degrees in there. We know that these angles in here are 30 degrees. What that means then is we can calculate the measures of these angles here. We know they're going to be congruent because it's an isosceles triangle. So if we take 180 and subtract 30 from it, that gives 150. So we know that these two angles are going to have a measure of 150 degrees together. So we take 150, we divide that by 2, and that gives us 75 degrees. So we know the measure of these angles are 75 degrees. Now, since these are all parallel lines, because these are isosceles trapezoids, we can determine then that the measure of this angle here is 75 degrees, and the measure of this angle here is 75 degrees because this is a transversal crossing 2 parallel lines, and these angles would be considered corresponding angles. Finally, here we can find the measures of angle C and D because these are supplementary to one another. So if we take 180 degrees and subtract away 75 degrees, that gives us 105 degrees. So the measures here in this case, the measures of angle A and B are 75 degrees, and the measures of angle C and D are 105 degrees. Here are 2 more theorems or properties about the diagonals of isosceles trapezoids and the diagonals of a kite. The diagonals of an isosceles trapezoid are congruent. Now that's similar to the theorem that stated that the diagonals of a rectangle are congruent. So very similar to that. In fact, exactly the same, except it's talking about an isosceles trapezoid. The next thing is that the diagonals of a kite are perpendicular. Now, the diagonals of a rhombus are perpendicular. And really, you could say that that's a special kind of kite. So let's see how to use these theorems and properties as to solve problems. Example 3. We're asked to find the measures of angle 1, the measure of angle 2, and the measure of angle 3 in the kite. So we know that quadrilateral ABCD is a kite because it tells us the congruent sides are marked. So then we need to start figuring out the measures of angles here, and that should be a pretty easy thing to do. The first thing would be the measure of angle 2. I think we're going to start with the measure of angle 2 is equal to 90 degrees, and that's because of the theorem we just read previously in this video geometry lesson, that the diagonals of a kite are perpendicular. Now we're going to find the measure of, angle 3. The measure of angle 3 we're going to calculate or find because of the triangle angle sum theorem that says the sum of the angles of a triangle are 180 degrees. Well, we're going to have to add 90, because we know this is a 90-degree angle, to 170, or not 170, but 275. And that gives us a 165. And then we take 165 and subtract it away from 180. When we do that, we get 15 degrees. So the measure of angle 3 is 15 degrees. And finally, we're going to find the measure of angle 1. And the measure of angle 1 is going to be 75 degrees. And that's going to be mainly due to corresponding parts of congruent triangles. We'd be able to prove that these two triangles are congruent. Therefore, the measure of angle 1 and this measure down here, marked 75, would be the same. So there's using a property of the diagonals of a kite are perpendicular to help you find the measure of angles when given the measure of one angle.